We'll go ahead and get started. Today is the second week of the nickel lab. Last week you ran this reaction. You made the nickel complex that's shown up there. The nickel ENX, water Y, sulfate, and ZH2O. So this week we're trying to figure out what that formula is. What are X, Y, and Z? What is the ratio of nickel to ethylenediamine? How many waters do we have in the coordination sphere? How many do we have as waters of hydration? And so basically, how do we do this? You should be able to answer this question, at least in general strokes, if you were asked on a final exam. Remember, when we're looking at this formula, we're talking about a ratio of either atoms to atoms or atoms to ions or to whatever the ligands are. We often express it, though, as a mole ratio. So if we can find out how many moles of nickel we had, how many moles of ethylenediamine, how many moles of sulfate, how many moles of water, we've got the formula. So basically what we're trying to do is determine the moles of each of those, get that mole ratio, and from that we can get a formula. For the nickel, we're going to be doing this gravimetrically. We're going to precipitate that nickel in a form you've seen before, the nickel DMG, dimethylglyoxine. During the qualitative analysis, you added DMG, some dimethylglyoxine, to your unknown, and also to the standard that you did the first week. You added some to that. If you had nickel, you got a red precipitate coming out of that. And of course, if you didn't have nickel, you did not get the precipitate. We better have nickel today, so you should get lots of red precipitate. We can collect that, weigh it, and then we can determine how much nickel is present in that way. Sulfate and nickel are going to have to be equal in terms of the mole ratio. The nickel is a +2 ion, sulfate's -2. You have to have 1-to-1 to balance those charges. So whatever we have for nickel, we have to have an equal amount of sulfate. So those are pretty straightforward. The ethylenediamine, we're going to be determining titrometrically. Remember that the ethylenediamine is a base. It is similar to, let's see if this is going to work for me. It is similar to ammonia. Have you guys done acid base in lecture? So you should be then familiar that NH3 ammonia is a base. We have that lone pairs. It's called a Lewis base, but it is a base. When we're doing the ethylenediamine, we have very similar structure. Instead of 3 hydrogens, we've got a couple of carbons attached to that, but still a base. So we can titrate this with an acid, similar to what you did 2 weeks ago with the standardization of sodium hydroxide. So we'll be doing a titration to figure out the amount of ethylenediamine that's present. And then what's left is the water. We just do the water by difference. If we know how much stuff of the complex we start with, and we know how much nickel we have, how much sulfate, how much ethylenediamine, whatever is left has to be water. And so we can just do that by difference. So today's experiment, you're going to be working individually. Last week you worked in pairs to make the nickel ethylenediamine complex. You're going to be working individually. You're going to share that. The stuff you made, you should have probably close to 2 grams of product. You only need 0.3 of a gram for this reaction, so you and your partner can each do 2 or 3 reactions with this without any problems. There's plenty of the material. So the first thing you're going to do in lab is get the mass of product that you made. So you made it last week. It was still wet. So you didn't weigh it at the end of the lab period. You just put it in a beaker, stuck it in your drawer. By this point, all of that water should have evaporated, the water that it was just wet with. Obviously, the waters in the formula will stay there. So you're going to weigh it, get your yield, and then you're also going to calculate a percent yield. Then you're going to take 0.3 of a gram of that material, and it doesn't have to be exact. If you have 0.31 grams, 0.29 grams, you're close enough. 0.28 grams, close enough. It doesn't matter exactly how much you have. You do want to know that mass exactly, though. So you do want to weigh it and then write down the exact mass that you have. This PowerPoint, by the way, I put a copy in both my folder and Mr. Leonard's folder, so you'll have access to this. You can just download it and look through it. I see people taking pictures. If you want to, that's fine, but you can get this as well. So the first step then is going to be the titration. Just as you did last time, you've got your burette. You're going to want to prep this. Hopefully they're clean, but still it wouldn't hurt to rinse it with a little bit of distilled deionized water. And then we always rinse the burette with a little bit of our titrant, whatever it is that we're going to be titrating it with. So in this case, we're going to be titrating with some hydrochloric acid. So you'll just pour a little bit of acid in there. You want to rinse the burette, same as you did last time, just tip it on its edge and rinse that with some of the acid, run a little bit through the tip, and then you can pour the rest of it out. We do this to clean it, but then also to rinse this with the acid so that the only contaminant in here now is the acid. If you simply pour acid into a burette that has other stuff, it could react and dilute the acid. Or if you wash it first, it still has water that will dilute the acid. And then you'll want to fill this up with some hydrochloric acid. Doesn't matter, just like with the standardization experiment, you don't have to get this exact. Just get it somewhere close to the top. You'll have plenty in here then. And we're going to do the titration. So we do want to get a little bit in that tip. Remember to debubble that. And then we're going to do our titration. The indicator we're using this time is not phenolphthalein. We're using something called bromocresol green. This has a basic or a deprotonated form that is blue and an acidic form that is yellow-orange. So we're going to put a few drops of this in, and you can see it went from that pale lavender color that it was initially to blue. This is the indicator we're looking at now. And so when you titrate, you'll want to have something white underneath this so you can see the color change more easily. And then just titrate and twirl or mix it while you're doing this. You may want to go a little more carefully than me, but with white you can see where the acid is going in that we're getting a bit of a yellow color. That will start to persist as you get closer to the end point. And the end point in this is a little squishy. With the phenolphthalein and the acid-base one that we did, the end point was very sharp. You went from a colorless solution when it was acidic until that one drop of the sodium hydroxide could convert it to pink. In fact, if you're really careful, often you can get it with just half a drop. You get it to the point where it's very faint, or pink is almost persisting, and then you can just wash a half drop that's hanging off the bottom of the burette to get that last one in. This one goes through a little bit of a green stage where you've got both forms, the basic form that's blue and the acidic form that's yellow. And at that point, you'll have a little bit of a green color. So it's not quite as sharp as the phenolphthalein, but you can get there, and you'll notice it's getting a little bit paler as I'm getting close to the end point too. So that helps when you're getting close. And you can see it's almost persistent there with the color change. And so you can get it there. See, it's just about persistent. So I think I may have just, nope, not quite. So you can see it was almost there. I'm going to add just a drop and see if we can get this to just that green color that you see in between. The green is the ideal, but if you do go over a little bit, this reaction is somewhat forgiving in that it will throw off your ratio, your mole ratio of nickel to ethylenediamine just a little bit. But remember, it's a whole number ratio. I thought I had it. Just went back to blue. That ethylenediamine to nickel is a whole number ratio, so if you are off a little bit, if you slightly over titrate and make it yellow instead of stopping at the green, it's not going to be an issue. You've got that green color there. This is what the endpoint should look like. I meant to wear a white lab coat so you can see that a little better. It is going back a little bit, might need one more drop, but this is what you're looking for. If you get this, you're there. If you over titrate a little bit, I'm going to go ahead and add excess. You go to this yellow color. That's not a problem because, like I say, if you're over slightly, you may get something like for your mole ratio of ethylene to nickel, might be 1 to 1.1. You're off by 10%, but you know what? It's still 1 because it has to be a whole number. So this one is somewhat forgiving, even though that endpoint isn't real sharp. So bromocresol green. But after you've done this, again, record your volume that you had at the end of the titration, and you recorded, of course, the beginning. You have the volume, the molarity of the hydrochloric acid on the bottle. Make sure you record that. You can calculate the moles of ethylenediamine. We will then use that same solution to precipitate the nickel. So you're going to add some concentrated ammonium hydroxide to this. It should turn back to blue. It says in the instructions if it doesn't turn back to blue, you can add more NaOH. Have you ever seen it not turn blue? I mean, we've still got bromocresol green. The ammonia itself should turn it blue. So just go ahead and add the 6 mils. If it doesn't turn blue, show it to us and be curious to see that. You shouldn't have to add more, but you're going to add this. The ammonium hydroxide is a very pungent material. We keep it in the hoods. We don't carry it around to our room, which is one of the reasons I didn't bring it in here. That and the fact that we're going to have to heat this stuff. But add it in the hood, and then once it's diluted, you can take it back to your workspace. But the concentrated stuff will clear your sinuses, it will burn your throat, your eyes will run. It's not pleasant stuff, so measure it out in the hood, add it, and then take it back to your workspace. Then we're going to heat it to get it nice and hot. It doesn't have to be all the way to boiling, but you want to get it hot. This ensures that we're isolating that nickel so that when we add the DMG, it's going to precipitate. Add it slowly, just as you did with the ethylenediamine last week. Just add a little bit at a time, keep swirling. As you add it, you can start adding a little more quickly afterwards, but go kind of slowly to start. And then once you've added all the dimethylglyoxine, the nickel should be precipitated. You're going to filter and wash it. I didn't bring a Buechner funnel, but same thing you did last time. You use the Buechner funnel and the filter flask, put a piece of filter paper in there. The instructions, of course, tell you to pre-weigh it, and then you're going to turn on the water. If you had an aspirator last week that didn't work, you might want to go to a different sink. But just like last time, you'll take one of these little pipes and stick that in so that you fill the sink with a little bit of water so it doesn't splash. And then turn the water up all the way when you do the filtration. You want as good suction as you can get. And you're good, after you filtered all of it, you're going to wash it with a little bit of water and then a little bit of ethanol. The ethanol will help remove any excess DMG, and we do use an excess so we make sure we get all the nickel out. The ethanol will help remove that, but also the ethanol will remove the water. And then ethanol is more volatile. We want to dry that, so once you've filtered it, if you see no more liquid coming down or it looks sort of dry on the top, you can stick it in the drying oven. We've got 2 of them in the labs, and just stick it in the beaker, stick it in the drying oven, and it says to wait 20 minutes. Have you ever tried less? I can't imagine ethanol is going to take that long in a 100-degree oven.
You might want to check it after 10 minutes. You'll see it looks like a potato chip coming, separating from the paper.
Yeah, it's going to be pink. It should look dry and brittle, and it may well be peeling off that paper as well. Give it 10 minutes, but after 10 minutes, I would think all the ethanol is going to be off, especially since it's as hot as we have the oven. But check it. If it looks like it might still be wet, leave it in for another 10 or 15 minutes. The oven is at 100 degrees Celsius. That's the temperature of boiling water. If you're not comfortable sticking your hands into a pot of boiling water, you don't want to grab your flask with your hands either. You should have some tongs in your drawer. Use those to remove the beaker and then set it on your desk and let it cool. But during that 20-minute heating period, that's a good time to clean everything else up, because at this point, all you're going to need to do is pull this out, let it cool, and then you're going to weigh it. And once you have the mass, we're done in lab. So Most of this won't take too long. You'll probably be a little slower with the titration than I was. You'll want to be careful with it. When you've done a few of them, you can go more quickly. But it still doesn't take that long. Making the DMG, you've got the heating period. That's going to be a little bit, we've got a lot of calculations to talk to, so don't get ready to run yet. So we are going to be finishing up. It will take a good part of the period, especially with that 10-15 minute heating. So then we have to do all our calculations. So with the nickel sulfate, again, we want to find out what that mole ratio is. We did the ethylenediamine titration. For the molarity, you want to copy that down. I've got a sample one here that's not from this sample. Molarity and volume. Of course, the volume you're measuring is in milliliters, but molarity, the units are moles per liter. So we need to have our volume in liters, so those will cancel. And then molarity times volume gives you moles. So anytime you're working with solutions, we use molarity times volume rather than density and a volume or mass. Molarity times volume, multiply them together, and we would get moles. And this is the moles of ethylenediamine that was in that 0.3 gram sample. So now we know the moles of, this is moles of hydrochloric acid. We have to calculate moles of ethylenediamine. But remember this equation, for each 2 moles of HCl, we have 1 mole of ethylenediamine. So that mole ratio, we're going to have to divide that by 2 to get the moles of ethylenediamine. And then the water we're going to be getting by difference in mass, so we do need to calculate mass as well. You should all know how to do that. You take the moles and use the molecular mass or the molar mass, and you can get grams of ethylenediamine that was in our sample. So if we had 0.291 grams to start with, 0.1 grams of that is our ethylenediamine. Then we go for the nickel. Same sort of thing. We make the nickel dimethylglyoxine. You're weighing that at the end. If you get 0.239 grams of nickel dimethylglyoxine, we can calculate moles. And again, everything is in mole ratios when we deal with chemistry. So we've got grams. We use the molar mass to get moles of nickel DMG. And nickel in DMG is 1. We have 1 nickel for each mole of DMG, so it's 1 mole of nickel. So those values are equal, and we have the moles of nickel. But again, we want mass of nickel so that we can determine the amount of water. And here we use the molar mass of nickel, or the atomic mass that you would get off the periodic table. And that gives us the amount of nickel that's present. So now we know the mass of nickel, we know the mass of ethylenediamine, we need to know the mass of the sulfate. Same process. Moles of sulfate, though, as I mentioned at the beginning, is equal to the moles of nickel. At a 2 plus ion, a 2 minus ion, the charges have to balance, and so the moles have to be equal, and so we know the moles of sulfate. But again, to get water, we need mass, so we would use the molar mass of the sulfate anion to get the grams of sulfate. And then that leaves water, and that we just do by difference. Again, if we weigh our complex at the very beginning, we've calculated the mass of nickel, we subtract that, subtract out the mass of ethylenediamine, subtract out the mass of sulfate, all that's left then is water. And then we can also calculate moles of water from that. And we'll talk about distributing that between the 2 waters. We have water hydration, and we also have water that's in the coordination sphere. We could write formulas in, using our mole ratio like this. Technically, this would be correct, although chemists don't like this, and we tend to count off if you don't normalize it, meaning you set it to whole numbers. So how do we get a whole number ratio from a fractional one? Well, you simply divide all of these numbers by the smallest. Dividing the nickel by itself gives us 1. And then we divide everything else by that same value, and we find out we have 1 nickel, 2 ethylenediamines, 4 waters, 1 sulfate, which gets us partway there, but we still don't know. We've got y and z together is 4, but is this 4 and 0? Is it 1 and 3, 2 and 2, 3 and 1, 0 and 4? We don't have that ratio. And for that, we need to look back at the structure of the nickel and then figure that out, and also the structure of the ethylenediamine. Nickel will form 6 bonds. So we've got 6 coordination sites in that nickel. It can form 6 bonds then. And so if we think about it, the ethylenediamine can form bond at 2 sites. It's bidentate. And so if we have one ethylenediamine, it's going to connect to 2 of those bonds in this fashion, which means we still have 4 available, so those 4 will be filled with waters. So if we have one ethylenediamine and 4 waters, all 4 waters are going to be in the coordination sphere, and we have 0 waters of hydration. So we would have Y is 4, Z being 0 in that case. If you have 2 ethylenediamines, again, each one takes up 2 sites, meaning we've got 2 left. So we'd have 2 waters in the coordination sphere. Our Y would be 2, and the Z would be 2 for this particular complex. You may actually have something else for water. If you have 5, you'd have 2, and then dot 3 H2O. And of course, if you have 3 ethylenediamines, then you don't have any bonds left to the nickel. So for this case, your Y would be 0, and all of your waters would be waters of hydration. And so for the calculations we did, we had 2 ethylenediamines, which means this would be our formula. We've got 2 waters in the coordination sphere, our Y is 2, and we have 2 waters of hydration. And again, you may have more waters, you may have less than what I have here, and then how you partition those waters between the 2 just depends on how many bonds to nickel you've got available. Ethylenediamine with the tris, ethylenediamine, you've got 3 ethylenediamines, all the coordination sites are taken, all waters hydration. If you have the bis, the 2 ethylenediamine, you've still got 2 sites, and the rest of the waters will be waters of hydration. And then you also have to calculate percent yield. For that, you need theoretical yield. I didn't do slides for that, but I'm assuming you all know how to do that. Based on the amount of nickel you started with, calculate a theoretical yield of the complex. And of course, you can't do that until you know this formula. Once you know that, calculate the molecular weight of this. Don't forget your waters of hydration. They do have mass. They're part of that molecule's molecular weight. So you can determine the molecular weight from that, and then calculate theoretical yield. And percent yield is just actual over theoretical. So doing percent yield, and is long enough. Percent yield is equal to the actual. So this would be what you weigh at the beginning of this lab period divided by the theoretical, which you can determine after you know what your product is. And of course, make it a percentage where you multiply by 100%. Any questions?